Okay, the diagram shows a Ferris wheel doing uniform circular motion. A passenger car goes through an angle of 70 degrees in 1 minute. Calculate the angular speed of the Ferris wheel in radians per second. So what is angular speed? So the units actually give it away here. It's measured in radians per second. Now radians is a unit for angle and seconds a unit for time. So therefore we can come up with the definition, which is going to be angular speed is equal to the angular displacement, angle turned per unit time. Angular speed is given this symbol here, omega. It looks like a W, but it's actually a lowercase omega. And sometimes angular speed is referred to as angular velocity or angular frequency. Okay, but still measured in radians per second. So in this case, it's turning to 70 degrees in 1 minute. So we're going to have turned that angle. So here's the equation for us. Angular speed here is angle in radians divided by time. So in this case, 70 degrees divided by 360 times 2 pi to turn into radians, times by the time in seconds, so that's 60 seconds, and that gives us the angular speed of 0.021 radians per second. So it's turning through 0.021 radians every second. Okay, a person is standing on the surface of Earth. Calculate the angular speed of the person due to the Earth's rotation about its own axis. So the Earth is rotating around its axis like this. Okay, and what do we know? We know that it takes 24 hours for it to rotate around its own axis. And if a person is standing on it, like say over here, then he's also going to take 24 hours to go around the circle like that, assuming he's not moving, he's just standing there. So the angular speed, which is given by this equation here, now we know the time here to go around one whole complete cycle, that's the time period. So we know the time period is 24 hours. And what's the angle turn in this time? Well, it's going to do one whole circle around the Earth in that time. So it's going to be 2 pi in radians there. Okay, so this gives us a very useful equation, okay, which you need to memorize, which is omega, the angular speed, equals 2 pi over the time period. Omega is measured in radians per second and time period in seconds. And so let's put this number in. So we've got 2 pi divided by 24 hours, 60 minutes times 60 seconds. And that gives us an angular speed of 7.27 times 10 to the power minus 5 radians per second. So not too fast, not turning around too much of an angle per unit time. Okay, so while we're here, we know that time period is equal to 1 over frequency. So if we put that in at the bottom of the equation, it gets flipped over and multiplied at the top, which gives us another good equation, but not as useful as the first one. Omega equals 2 pi f. The angular speed of a spinning wheel is 10 pi radians per second. That's basically like 5 complete circles in 1 second. The outer radius of the wheel is 0.62 meters and the inner radius is 0.58 meters. Calculate the linear speed, so that just means normal speed in meters per second, at the outer edge and at the inner edge. Okay, so we know the speed, one of the equations in circular motions, is the circumference divided by time taken to go around the circumference. So 2 pi r divided by the time period there. And we also just learned the angular speed, which we've got here, is equal to omega equals 2 pi over t. And as you can see, the only difference is that the velocity has an extra r there. So we can come with a very useful equation here, also worth memorizing. V equals omega r, where v is the speed in meters per second. Omega is angular speed in radians per second, and we've got the radius there. Okay, so let's put the numbers in here. So we've got the angular speed, which is 10 pi, times the radius at the outer radius, gives us a speed at the outer edge of 19.5 meters per second. And in the inner edge, the speed is 18.2 meters per second. Now this makes sense because on the outer edge, in the same time, for example, time to do one whole cycle, it's traveling a larger circumference, it's traveling a larger distance, so it has to be going faster on the outer edge. And the inner edge is not traveling as large of a distance, so its speed at the inner edge isn't as fast. But however, they both have to be spinning at the same angle per unit time, because if they had different time periods, so let's say it was traveling at, in a certain amount of time, one did a larger angle than the other, then they would move apart. So these particles in the spokes of the wheel here would move apart, so the bike would just fall apart. So this brings us to a nice important point here. Okay, particles in a rotating solid object or rigid object have the same time period, and hence they must have the same angular speed. For example, particles on a disk. So let's say you've got 2 fixed points on a disk. Now if one point went around at, let's say, 1 second, the other must also go around at 1 second. Otherwise these 2 points, the angles between them would be increasing and they'll be moving apart, so which means the disk will basically tear up. let's take an Earth as an example here. So let's say we've got a country here and a country here. If obviously one country will take 25 hours to go around the axis of the Earth, if the other country took, let's say, 23 hours, then they'd be moving apart. Okay, so that can't happen in a solid object. Okay, so this is not true when the objects aren't attached. So for example, the Earth can take 365 days to go around, and and Mars here takes 687 days to go around. So that means they can have different angular speeds, and in fact they can even have different speeds around the sun as well.